Right, back to exponentials again now, but this is still using logarithms to solve an exponential equation. So you've seen some of these before, especially this kind of example, but the main use for logarithms in terms of exponential functions is to be able to find the exponent. In other words, to find the index. So if we've got a missing value in our index, we need to use logarithms to basically bring it down into the equation and we can solve it from there, okay? Right, this question here is a little bit more difficult because it's not actually giving us the equation in the first place. The next question, I think I'm going to show you an example where it does give you the equation. But in the first instance, anyway, question A here is actually just a National 5 question, okay? This is basically using compound interest to find a future value of something. And then in the second part, we're going to use basically what we created in the first question to find a different missing value, okay? But after 10 years of investment, what we're going to have is the £4,000 is going to increase by 2.45% each year. And because it's for 10 years, we don't want to have to do this 10 times over. We don't have to work out 2.45%, add it on, and then take 2.45% of the new value and do that 10 times. There's a quick way. If you remember back to National 5, you can use indices to help you. In which case, what we're basically saying is we're keeping that initial £4,000, plus we're going to gain an extra 2.45%. So we'll keep the initial 100%, an extra 2.45% will be a total of 102.45%. And that as a decimal is 1.0245. That's what we're going to calculate. That's what we're going to be what we're going to have in our bank account at the end of each year. And we want to do that calculation 10 times. So 1.0245 to the power of 10. We'll do it all in one fell swoop. £5,095 and 41 and some more pennies. In other words, the investment is worth £5,095 and rounded up would be 42p. So the point is, if we had this equation here, okay, and we wanted to actually find the value of 10, so say we knew the overall investment, but we didn't know the length of time it was taking, then we would have to use exponential or logarithmic rules to be able to find it. And that's basically what question B is doing. How long would it take the investment to increase by 50%? Okay, so the first thing we want to do is work out what 50% of £4,000 is and add it on. Okay, that's quite easy. 50% is just £2,000, in which case we want to know how long it's going to take to get our overall investment to £6,000. So very similarly to the equation that we wrote in part A, we basically want to have £6,000. It's based on our £4,000, increasing by 2.45% each year, but we don't know for how many years that would be. So that's where our n value comes in. So as I say, very similar to a National 5 question, but you never actually had to do this in reverse. But now we've got to do this calculation, okay? Right, a couple of things in the way this is written, and this is where a lot of people might get confused. Don't do 4,000 times by 1.0245, okay? Obviously, because the 1.0245 is to the power of n, we can't do that first. So we have to do something else with the 4,000. The best thing to do is to move it to the other side. And when we do that, you'll start noticing something. 6,000 obviously divided by 4,000 is 1.5, okay? That's the 1.5 times our investment. And that equals 1.0245 to the power of n. Right, now in order to find this n, again, this is what I mean by bringing it down. We want to use laws of logarithms to be able to do this. In other words, we want to take the log of both sides. Or if you have the right kind of calculator, what you can do is just rearrange this into exponential form. So if 1.5 equals 1.0245 to the power of n, then n will equal the log of base 1.0245 of 1.5. And if you've got the right kind of calculator, you can just put that straight in your calculator, okay? And I'm going to come back to this in a second and do it a different way, okay? But if we have the right calculator, this is just a case of pressing numbers in our calculator and to give us an answer of 16.751. Right, and this is one of these kind of questions where you have to think about how the rounding works here. The way interest works is it's per annum, okay, and it's added at the end of each year. And if it's added at the end of each year, then after 16.7 years, okay, they won't be adding any extra money. It will only be after 16 years or 17 years. So clearly after 16 years, we won't have the £6,000, but after 17 years, we will do. So the investment will increase by 50% after 17 years, okay? Right, if I go back a little bit, and we go to this point here, if I didn't have the calculator whereby I could change the base, I would have to approach this slightly differently. Okay, and I can't rub out that red line now, so I'm just going to have to deal with it. But what you can do is you can take the log of both sides. And what we do is we take the log of base 10. And the reason for that is that's the log in our calculator. Okay, so if you have a calculator that doesn't allow us to change the base, then the only thing we can use is the log button, and that just means log of base 10. So if I do the log of base 10 of 1.5, in the same kind of way, but the opposite as the previous video that I did, we can now take the log of base 10 of both sides, and this would be log of base 10 of 1.0245n to the power of n, sorry. And the idea of this is that this now allows us to move the n to the front, in which case it's more like something we can deal with. So log of base 10 of 1.5, that's just a number. I can stick that in a calculator and work that out. But on the right-hand side now, I can stick the n at the front, and I can have the log of base 10 of 1.0245. And now if I want to isolate the n and get it by itself, I could just divide both sides by log of base 10 of 1.0245. So I'd have the log of base 10, and this is where I'm going to start running out of room, of 1.5 divided by the log of base 10 of 1.0245. And when I stick that in a calculator, I'd still get back to that same answer. Okay, but if you're lucky enough to have one of the calculators that's got the button that looks something like this, log of base box, and then another box, whereby you can change the base of the log on your calculator, then you don't have to go through that whole rigmarole. You can just actually change it at this stage into a logarithmic form. Okay? Right. Skip. That's that button. Yeah, I didn't have to draw it. It's that button there. Okay? Whee! Okay. So this is more like what you've seen in a past paper. And if you've done any past papers, you'll have seen these because these are quite common. And it's basically dealing with, obviously, E. And you often see this minus KT. Okay, it's quite a common one that comes up. The K is basically just a constant. It's a constant number depending on the situation that we're dealing with. And there's lots of different situations. So this is cells dying. It might be population increase. It might be a case of money. There's lots of different examples that you can use this in, but here we have an experiment measuring the rate at which cells are dying. It is found that the cells are dying according to this formula, right? It looks complicated, but it's not too bad. CT is just the number of cells after T days, so T is obviously telling us the number of days, and C0 is the initial number of cells, okay? Don't be put off by these different letters and different ways of writing things. The calculator will do most of the work for us here. We've just got to be able to rearrange this. So given that the experiment began with 240,000 cells, so that's quite clearly going to be our C0, and half of the cells, that's going to be important because it's a number, this is maths, had died after 7 days, is obviously going to be our T. Determine the value of K, okay? So it's just a case of putting this into the formula, and you pretty much get a mark for actually writing it in the formula in the correct way. So because we want half of the cells to die, and given that we're starting with 240,000 cells, then clearly we're looking to have 120,000 cells as our CT, okay? So 120,000 equals 240,000 e to the minus 7k. So T was 7, so I've just rearranged it so the letters at the end. Now I need to find this value of k, and again, this is where logs come in. Right, I'm going to persist, well, so this doesn't matter actually in terms of changing the base, because what our base is going to be when we take the log of both sides is log of base e. We've already dealt with log of base e, that's just a natural logarithm, okay? So we can divide by 240,000 first of all, just to simplify this a little bit, okay? And now it's just a case of obtaining that k, in which case we can rearrange this into a logarithmic form. So if we have 0.5 equal to e to the minus 7k, then minus 7k will equal log of base e of 0.5. And as I say, log of base e is just ln on your calculator, so that's fine, there's no problems there. So ln is 0.5, and then divide by the minus 7 will give us our k value, 0.09902. And I'm going to round this slightly. I might as well have rounded it to two significant figures, but I've written 3 there anyway. 0.0990. So this is my constant. This is the value that we always use. It's basically part of the formula. They're just being awkward at the start and not putting it in so that you can calculate it. But now, for part B and any other calculation that we want to do, this is our set k value. Okay, so we want to calculate the time taken for the cells to reduce to 20% of the initial population for this second part. So similar to that last one, we had half. Now we're going to have 20%. So the first thing we want to do is find 20% of 240,000, which is 48,000. Okay, and we can use our formula now with k replaced by minus 0.099. So now putting in our values, our CT is 48,000. Original value of number of cells was still 240,000. We've got our K. Now we're just going to try and find our T. Okay. So solve this in the same way we solve other equations. Move most things to the other side apart from the letter that we're trying to find. So shift the 240,000 over, 0.2. And now it's a case of rearranging in exactly the same way as we did before. Okay, minus 0.099t is going to equal log of base e of 0.2, in which case t is going to equal log of base e of 0.2 divided by minus 0.099. Stick it in your calculator as ln. It comes up as 16.2569. Right, given this situation, it's not such an issue that we can round because the cells are just dying all the time. As I say, with an ICE or something like that, it only really gets added each year, so we have to think about the rounding there. But here, it will take approximately 16.3 days for the cells to reduce to 20% of their original number. We couldn't round down to 16 days because that's not strictly true. It's taken a little bit longer than that, okay? So think about your answer there. Right, that's a past paper question. If you want to give it a bash, I'm just going to leave it there.